Numerical Computation, Chapter 4, Video 9. In this video, we will go through the derivation of the Romberg algorithm. The derivation is based on using trapezoid rule as the base approximation. So the starting point is that it is given a sequence of computation for trapezoid rule using grid size and being halved at each step. And from previous video, we see that we could form a new approximation by simply doing this manipulation of the trapezoid rule, and this will result in an approximation. This u here will be a fourth order approximation. Now, assuming using t of h half and t of h fourth, we computed u with h half. Then the error estimate for UH half takes the same form as UH here, except you put H to be H half. So we just copy this down and change H into H half. And now we perform a similar manipulation, and we want to cancel out the leading error term, which is the H fourth term here. What we could do will be we take equation number 4 and multiply it by a factor of 2 to the 4th, which is 16, and then we subtract equation 3 from it. Then you know these two terms will be gone. So all I have on the left-hand side will be 2 to the 4th minus 1 times the integral. That's what you want to find. And this will equal to 2 to the 4th times u at h half minus u at h plus. Now these two terms cancel each other, and what we have will be something of h6 times some constant. So let's denote that constant, a tilde prime 6 and 6h to the 6. Then you can divide both sides of this equation by the factor of 2 to the 4th minus 1, namely 15. And then you get a 6th order approximation to the I over here. Okay, let's denote that approximation v of h. That's exactly 2 to the 4th u h half minus uh over 2 to the 4th minus 1, and which can be written into this form. That's just an algebraic manipulation. And then plug that back in. Then we have the integral equals to vh plus something that starts with h to the 6 as the leading term. So this v here actually becomes a 6th order approximation. Wow. One has to say now v now is way better than u, because u was only 4th order. As we can imagine, one can keep doing this several layers using 2 of the previous value to produce 1 for the next layer of value, and keep doing it until you run out of data or your desired accuracy is reached. And this gives the Romberg algorithm. Let's look at the detail of the algorithm. So we would set h equals to b minus a, that's the length of interval, and we compute the trapezoid rule using h half, h2 to the power 2, h over 2 to the power n plus 1 such trapezoid approximation. And this will be assigned as the first column of a matrix that we're going to generate. And this is called R matrix. So R of 0, 0, 1, 0, 2, 0, and 0 will be filled, initialized by the trapezoid computation. Then using these as the starting value, like the first column here, and one can generate a Romberg triangle. And that is using these two, I could compute a better approximation, then I call it R11. And using these two, I can also produce a better approximation called R21. So this would be actually our u of h, and this will be our u of h half, and u of h fourth, and this will be u of h divided by 2 to the power n. And then using the information in this column, the u column, I could use these two to generate the v as we denoted, and this will be the v of h, and I call it R22, and then use these two to compute another v of h half, and so on and so forth. And you see you can repeat this until you complete this triangle and you reach to the final number, this R and n. So all these numbers are approximations to the integral you wanted to compute. Which one will be the best? Well, of course, the final one. Okay, let's write out the general formula. So each entry Rmn is computed by using two entries from the previous column, right? So exactly into this form. We are familiar with this form, except now it's written as R, not U and V. So at level m, you have to change the power into 2 to the 2m, not 2 anymore, or 4, because it increases. We know from our discussion earlier, that is, at level m, the order of your approximation will be 2m plus 1. Right, so when m equals to 1, that's a fourth order method, that's the u. When m equals to 2, that's the sixth order method, that's the v we have seen. So for the columns with a higher index, and you get a higher order method. Well, we also noticed that the algorithm actually could be done either column by column or row by row if you construct the triangle in the way we illustrated in the previous page. So here is a possible pseudocode for the program Romberg, which uses column by column algorithm. So you will have a homework problem asking you to code a Romberg algorithm, and you could use the pseudocode as a starting point. So what you have to do here will be basically follow the algorithm. So what you do first, this part, is to generate the first column of your Romberg triangle using the recursive trapezoid. See, so the next level is copying the first one, and then you half the h, the interval size, and then you add up all those that are newly inserted points to make the code more efficient. So after you generated the first column, then you go through the rest. You can go through column by column, starting from the second column to the last one. And in each column, since it's a triangle, you have a double for loop. The second one was starting from only j to n, the lower part of the triangle. And this is what you have to compute to fill in. Okay, so hope this will be helpful for your homework. See you next video.